Welcome back to Math 124. Today's topic is confidence intervals of proportions, how to calculate them. As we have been working with confidence intervals in StatKey, we have used this general formula for a confidence interval without really identifying it, but that formula is whatever sample statistic you are working with plus or minus z star times the standard error. As we have been working with StatKey, we have allowed it to provide us with the standard error. And for a 95% confidence interval, only for a 95% confidence interval, we have set that z star at 2 because we've said 95% of the data is between plus or minus 2 standard errors from the mean. Today, as we talk about calculating a confidence interval, we are going to get more precise values of z star to use, and we are going to calculate the standard error rather than letting StatKey do it for us. Those formulas will differ depending upon which sample statistic we are studying at the time. Today, we're going to be working with a proportion, a sample proportion. So we are going to use, for our standard error, a modification of the formula that you saw in the last video when we knew the population proportion, and we were forming a sampling distribution and finding its standard error from that known population. However, now we're talking about what happens when you just have a sample and you're trying to infer something about the proportion. So we don't know the population proportion. We are going to build our standard error based upon our sample proportion. So everywhere you saw a population proportion, a simple p, in the previous formula, you are now going to see a p hat. To understand how we will get a more precise z star value, we will first have to look at the standard normal distribution. At the bottom of your screen and written on the graph itself, you will see reminders that the standard normal distribution has a center or a mean of 0 and a standard deviation of 1. So we go out -1, 2, 3, -4 on this graph, standard deviations below the mean, and up to +4 standard deviations above the mean. Here again is the standard normal distribution with a mean of 0 and a standard deviation of 1. So 2 standard deviations actually puts us out here above the mean and here below the mean. But the area between those two red values is where 95% of the data is located. The 2 that we generally use as being the boundaries of the middle 95% of the data is actually an approximation. As you can see, the value down here, 1.960 in the positive direction and negative 1.960 in the negative direction, is a more precise value of the boundaries for 95% of the data, or 95% of the area under this curve. Now, why is it a little bit different? Because we've been approximating, right? And because we haven't been using this perfect normal. We've been recognizing that our data is approximately normal. When we are doing calculations, we are going to base our calculations upon data obtained, and upon the values obtained, rather, from this perfect theoretical normal distribution, whose equation is... Do not pause the video to copy down this equation. I will not be holding you responsible for memorizing or using this equation. We will let StatKey provide us with the z star values we need based upon this equation, but without us doing the tough calculations. So what is the z star value for 95% of the data? It is right here, 1.960. So when we are trying to find a 95% confidence interval for a proportion, we will use our sample proportion plus or minus 1.960 times everything under that square root. So there it is. Let's look at a specific example and actually do the work. In 2007, 216 Americans out of a sample of 1,350 Americans supported abolishing the penny. Let's calculate now a 95% confidence interval for the proportion of Americans in 2007 who supported abolishing the penny, our smallest coin, only worth 1 cent. First, we need to calculate the proportion. So to find our p hat from this sample, we will take the number of Americans in the sample who supported abolishing the penny, getting rid of it, okay, and divide it by the number of Americans in the sample, and that comes out to 0.16, 16%. This is the proportion of the people in the sample who supported abolishing the penny. Before we go on, we should perform the tests that tell us whether or not we have enough individuals in the sample for this proportion to make the calculations we're about to do valid. In other words, let's perform these two tests to see if the values that we have, sorry, let me get the hats on there, see if the values they produce are greater than or equal to 10. So 1,350 times 0.16 and 1,350 times 0.84. When we do those calculations, the values are 216 for the first case and 1,134 for the second. So yes, both of those are much greater than 10, so we can go ahead and perform our calculations. Let's make a little room here. Now, we already have p hat to perform our calculations. We will also need the value 1 minus p hat, because that's what we're going to need to calculate our standard error. That value is 0.84. We also need to recognize that n, the number in our sample, is 1,350 individuals. And then we need our z star. Because we are calculating a 95% confidence interval, our z star value is 1.960, right? We are going to refer to this formula, p hat plus or minus z star times our standard error, which we calculate using p hat times 1 minus p hat over n. For the values we have, this means that we will have a lower bound of p hat 0.16 minus 1.960, our z star value, times the square root of p hat, which is 0.16, times 1 minus p hat, which is 0.84, divided by the number in our sample. That's the lower bound. Okay, the upper bound, I'm going to have to write this a little bit smaller, will be 0.16, our p hat value, plus our z star value times our standard error. 0.16 times 0.84 over 1350. Remember the terminology we used when we were working with StatKey and using the 2SE approach? We said 2SE was the margin of error, since we have replaced the 2 with a more precise z star value, and we are now calculating the standard error. This entire 1.960, etc., is our margin of error, or as I have abbreviated it for you, our MO, our margin of error. Now, we could just calculate the lower bound completely all at once and the upper bound completely all at once. But I would like to go ahead and separate the margin of error and talk about how we can report our confidence interval in a couple of different ways. All right, so our lower value is 0.16 minus 0.0196, and then we take our sample proportion and we add our margin of error, 0.0196. When we round to the thousandths place, we get proportions of 0.140 as our lower bound and 0.180 as our upper bound. How can we express this when we are telling people what our confidence level is? So we can say that we are 95% confident that the proportion of Americans who support abolishing the penny is between 0.140 and 0.180. However, usually when we are speaking to the public, we say things like we are 95% confident that the proportion of Americans who support abolishing the penny is between 14.0% and 18.0%. Or we could say that we are 95% confident, etc., 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 is 16.0% plus or minus 2.0%. Any one of those three ways to state the confidence interval are fine. We stated the confidence level and the interval in some fashion. But wait a minute, what happens if we don't want a 95% confidence interval? What if instead we want, say, a 90% confidence interval? Well, now we need to find a different Z-star. So let's go to stat key. So I search for Lock5 stat in Google, and there it is, stat key. Now that it has loaded, I am going to go down here to the theoretical distributions, and because we are working with a proportion, we're going to use the normal distribution. So let's click on that. And it's loading. All right, there is our normal theoretical distribution. We are going to find the middle 90%, so we're going to click two-tailed, but this is set for 95 automatically. So what we need to do here is click that box in the middle and then enter the new proportion. 0.90, return. And now we have our new Z values. Even though stat key gives us both a lower bound and an upper bound, we will be using the upper bound because as we add and subtract the margin of error, the negative case is taken care of by the formula. So 1.645, that is the number I want you to remember. 1.645. That is the Z-star value. So our interval will look like the proportion, the sample proportion, minus the Z value, 1.645, times the square root of our proportion, our sample proportion, times 1 minus our sample proportion, divided by the number in our sample. The upper bound of our interval we will find by adding the margin of error instead of subtracting it. Okay, there we go. Over 1350, and that's the end of the confidence interval. Okay, let's calculate that. So our margin of error is now 0.0164. Okay, so that's our margin of error. Here's our margin of error again, 64. On this side of the interval, we are subtracting it, and on this side of the interval, we are adding it. We can now say, based upon the interval we just calculated, we are 90% confident that the proportion of Americans who support abolishing the penny is between 14.4% and 17.6%. We could also express the bounds as 0.144 and 0.176, or we can use the phrase is 0.16 plus or minus 0.016. You may express your proportion and your margin of error in decimal form or in percentage form as long as you are consistent. However, there is a key bit of information that is missing from all of our statements of this confidence interval, and that is we are 95% confident that in 2007, the proportion of Americans who supported abolishing the penny was 0.16 plus or minus 0.0016. Now, 16% of Americans is not very many Americans. However, a penny is worth even less now than it was then. So maybe it's time to ask this question again. Now, to answer this question, we would have to decide how to take a representative random sample of Americans, and we would have to define Americans. Do we mean residents? Do we only mean citizens? Do we only mean Americans? But just in general, what we are interested right now is how do you calculate a confidence interval for this? So let's imagine a U.S. senator wants to make a name for himself or herself by promoting the abolition of the penny. Now, it could be a really wise political move if a lot of people support that, but it could be disastrous if they don't. So this senator wants to be very, very sure that people really want to abolish the penny before any move is made in that direction. But also, we want to be very precise about the number and have a small interval. That 2% margin of error, okay, the MOE or margin of error of plus or minus 2%, that's not bad. That's really not bad. However, to get a higher confidence level and a small margin of error is not an easy thing because as the confidence level goes up, the margin of error increases. So how could we get a high confidence level with a small margin of error? In fact, so that it does not change from the previous study, it's approximately 2% margin of error. One way you can do that is to take a larger sample. How large a sample? Oh, the previous study was already well over 30, and it passed our n times p and our n times 1 minus p tests. And it would for this as well. But that margin of error is going to change a little bit. So what size sample do we need to use? That's the question. Okay, here is the formula we've been using for our confidence interval. However, we're trying to decide how many we want in our sample. We can find the Z star for 98%. We just need to go to stat key. But we don't have a sample yet. We don't have a p hat, nor do we know the population proportion. So we don't have a p either. What we're going to do to figure this out is we're going to estimate what our population proportion is. So there's a little tilde, little squiggle over the p's. That means we're estimating this proportion. Really, what we're interested in is that margin of error for that proportion, for that z-score. So we capture all of those, and we want the number in the sample in just the margin of error formula there. So what I've left there equals the margin of error. Your book just symbolizes that ME. That's fine, either way you want to do it. But we are looking for this N. So let's solve this literal equation, or this formula, for N. Just a lot of algebra. Divide both sides by Z star. That gives us the margin of error divided by our Z star value. Okay, that equals the square root of our estimated population proportion times 1 minus our estimated population proportion divided by N. Still, N is stuck inside that square root sign, so I'm going to square both sides to get it out of there. All right, so that gives me my margin of error squared over my Z star squared equals my approximate P times 1 minus my approximate P divided by N. Okay, so let's cross multiply. Okay, so if I cross multiply here, I'm going to do this, oops, and this. That means I will get on the left-hand side N times the margin of error squared equals, on the other side, z star squared times the proportion, approximate proportion, times 1 minus the approximate proportion. Okay? And finally, divide both sides by the margin of error squared. We will get n equals z star squared times the approximate proportion times 1 minus the approximate proportion divided by the margin of error squared. We know what margin of error we want. We know the confidence level we want, so we can go to stat key to find the z star. Now we have to decide what approximate proportion would be good for us to use. Luckily, we have a previous proportion. Remember, previously, our p hat was 0.16. Now, if the senator can discover that a large proportion of Americans now want the penny to be abolished, that's great. But if not, then the senator's just not going to do it. But this previous value is probably the best guesstimate, okay, of what it is currently. It's not likely that it's changed that much because Americans are pretty set in their ways. So let's go ahead and use that as our approximate p. Okay, maybe it's changed, maybe it's not, but if that is the value, how many people should we have in our sample to provide a good estimate? 98% confidence level and a margin of error of only 2%. Okay, well, let's plug in some values. N, don't know. Okay, we've got to go to stat key to get our z star. And here we are. Let's go to the normal distribution since we are working with, nope. Since we are working with a population proportion, we are going to use the normal theoretical distribution. I have clicked two tail. Now I'm going to click this 95% in the middle. Nope, I want 0.98. And I'm going to hit enter. And now I have my z star value, 2.327. That value is squared. I'm going to multiply that by my estimated population proportion and by 1 minus that estimated population proportion, and I'm going to divide it by the margin of error that I want squared. I only want a 2% margin of error, so that's 0.02 in decimal form, and I'm going to square that. Whoa, here's what I get on my calculator, okay, that I need 1,819.416144 people in my sample. This also tells me that I don't need just 1,819 people. I need more than that, but I'm not going to find 4/10 of a person anywhere. So I actually need to round up. When you are doing this calculation, you always round up to the next person. Okay, so 1,820 individuals need to be in my sample to get me, well, to get the senator, 98% confidence and a margin of error of only 2%. That's if the proportion is approximately what it was previously when the study was done. However, it might not be, right? What is the largest proportion that would give us the largest number we need in our sample? Okay, because we want to make sure we capture what we want to capture. Okay, so first we need to do a little more analysis with this formula that we have. And let's look specifically at the numbers that we put in. Okay, if we still want this 98% confidence, our z-star isn't going to change. We still want the same margin of error. But what if the proportion isn't 0.61? So if these two are staying the same, the only thing that we're thinking might change is this multiplication of p times 1 minus p. Let's do a few quick calculations and see what happens with different values of that p. So I'm going to come over here to the side, Okay, and we started with this, right? 0.16 times 0.84. So let's do that calculation, but let's also look at these calculations. What if it's 5%? Only 5% want to abolish the penny. That means 1 minus p is 95%. Oh, but if 95% of people want to abolish the penny, that means 5% don't. You see how those are actually equivalent? Okay, what about if 40% of the population wants to abolish the penny, then 60% don't. Or if 60% do, then 40% don't. Or if it is split right down the middle, 50-50, half want to abolish, half don't, I would not suggest the senator steps into that one. Okay, let's do the calculations. And there you have it. Which one is the biggest? The 50-50 split. In fact, that's the biggest it can ever be, right? All right, so if you want to make absolutely sure, if the senator wants to make absolutely sure that the results, that he or she can be confident of the results, 98% confident that it has captured the population mean with only a margin of error of plus or minus 2 percentage points, we have to change the p we're working with. Okay, instead of this, we're going to go over here and we're going to keep everything else the same. Let's see, I'll do this in blue so you can see the difference. Okay, our n has to equal 2.327 because we want the same confidence level. We want to multiply by 0.5, there's 0.5. Okay, and divide by 0.02 squared. That value on the calculator is 3,384.33. Nope, round up. 3,385 individuals would need to be in that sample to make sure that with 98% confidence, the population proportion of Americans who want to abolish the penny has been captured. Okay, that's all for this video. Thanks for sticking with me, and I will see you in class.